In the last video, we talked about the SIR model and what it means to go from susceptible, infected, and recovered. And also remember that we made some assumptions on the population that need to be met in order for us to apply the SIR model. However, now we're going to walk through the mathematics of the SIR model. And in particular, we're going to look at the rates at which each of the compartments, susceptible, infected, and recovered, the rates at which those change. Okay, so we're going to label the change from susceptible to the infected compartments as alpha, so we're going to say that that changes at a rate alpha, and we're going to say that the infected to the recovered compartment between there, that changes at a rate beta. Okay, so really if we have a rate going out that we say is a negative rate, and if we have a rate coming into the compartment, that's a positive rate because we receive people into that compartment. So if we look at the rate of change in the susceptible compartment, so S prime, the rate at which the susceptible population is changing, the rate at which people are leaving the susceptible compartment, we can say that that is alpha. But then as the population is leaving, we have to denote that with a minus sign. I prime, the rate at which the infected compartment is changing, that changes by, well, we have two things going on. We have some coming in, we have people coming in at a rate of alpha, and we have people leaving the infected compartment at a rate beta. Okay, so remember, a change coming into the compartment we say is a positive change, so I'm going to omit the positive sign, and if we have a rate and the rate leaving the population is a negative, so we say that the rate of change in the I compartment is beta, or alpha minus beta. Okay, and then the recovered population, we have people coming into the recovered population, or the recovered compartment, I should say, at a rate of beta, so this is just beta. Okay. But now we want to go ahead and figure out what alpha and beta are, what those specific values are. Okay, so what we're going to do is talk about beta first. Beta we call the recovery rate, so how fast people recover. Okay, so remember in this model that everybody recovers. Okay, so since everybody recovers, that means that only a % of the infected recover each day. And so suppose that the infection lasts for k days, since it's mild. Okay, so now thinking about this on a day-to-day basis, each day only 1 out of k people, or 1 out of k %, or 1 out of k recovers. Okay, so really what we're saying is that if we envision a line, okay, so a line, let's say that this is day 0 and this is day k. So at the end of day k, all the infected population would recover. So each day, if I divide this up into different tick marks, okay, so you can obviously count the days, but this would be 1 part 1 over k, and then this would be 2 over k. So each day an additional 1 over k recovers. Okay, and this 1 over k, we call that the recovery coefficient. Okay, and so really what we're saying is that the recovery rate, which is our beta, is equal to, and let me get a pen here, this is equal to 1 over k, but it's of the infected population, so we have to multiply by the infected population. Okay, and this is the recovery rate. Now what we'll see eventually is instead of writing 1 over k, we like to also write it as equals b I. Okay, so in essence what this means is that b, which is our recovery coefficient, is equal to 1 over k. Okay. This is just so we can do it in line text. We don't have to insert a fraction bar and make it look all different. We can just write it as BI. Okay, that's the recovery rate. And our other job is to determine alpha, which we call the transmission rate. Okay, so first thing, transmission varies jointly as the susceptible and infected populations, because remember, we have to have a susceptible population in order for there to be infection, and we have to have an infected population, and the infected compartment is influenced by the susceptible populations. Okay, so that means that using our definition of joint variation, this is equal to A SI. Okay, and A here we call the transmission coefficient. Okay, but I want to break A down. Okay, because sometimes we're given more information and we can't easily determine what A is. To determine A, we have to remember that a susceptible person has a certain percentage of coming in contact with the disease. Okay, so they encounter, they have a such and such percent of encountering a person with the disease. Okay, and then if contact is made, there's a percentage of that, percentage that they actually fall ill with the disease. So even if you come in contact, you may not get it. Think of the flu. You're around people who have the flu all the time, yet you don't fall ill, or you may fall ill. So meaning that alpha, this A value, we could really represent that, well, again, it's ASI, okay, but we could represent that A as P times Q, SI, okay. So the percentage of coming in contact times the percentage of falling ill with the disease, okay. And so in total, if we write our new model out, we get these three rate equations, which determine which describe the change in the populations over time. Okay, and now you can see that each one of them are changing in accordance with the population of one of the compartments. So these are actually nonlinear. Okay, nonlinear, remember, would mean a constant, or a linear change would mean a constant rate of change, so it would just be, say, A or B. Okay, so that's a brief rundown of the mathematics behind the SIR model, and in the next video we will look at an example that uses the SIR model.